just hide this.
So that we have to be official for a minute. Hi, everyone. Thanks for joining. So we're very excited to have Saar Tochner here today, who's joining us from the Hebrew University of Jerusalem, where he's advised by Saar. Oh, I guess not anymore. He's almost done with his PhD, just about to graduate. Congratulations.
Thank you.
And he's done a lot of really cool work on blockchains and privacy and incentives. And today we're going to hear about a differentially private payment channel network.
Thank you. Thank you. Thank you, Julia. Thank you all for joining this talk. This talk, I'm going to present a paper that I wrote in a joint work with Manda Tani and Saar. We're all from the Hebrew University. And the talk is called, the paper is called Twilight, a differentially private payment channel network. So this paper has got accepted to Usenet security that will occur in a month in Boston. So first of all, wait, is that the right one? No. So first of all, just a tiny bit about myself. I'm a PhD candidate at the Hebrew University of Jerusalem. A partial partial list about the papers that I published and I find very cool and interesting. So the first one is Twilight, which I will describe in a moment. So I'll just skip that. A paper that just got accepted to EC 22 like a month ago in Colorado. It's about manipulating the rate in blockchains. So logs, instead of creating in a specific rate, we were able to change the rate, which is cool because then we just use it to create arbitrage between different loans and earn a lot of money, which is wonderful. We also had a paper that's called route hijacking. This paper manipulates the routing mechanism inside PCNs. So we created channels in the network and then just make all the traffic on the network to go only through our nodes, which this is crazy because then this is loss of privacy and this is a single node that can execute denial of service to the network. That's also a very cool paper. The last one that I want to just highlight is how to pick your friends. That's a funny name about how to choose your peers in a general peer-to-peer network. We just used a generic game theoretic approach, but then we had to implement a Nash equilibrium with a support, a huge size support into a limited buffer, which created cool mathematics there, which also got accepted to AFT. Cool. So now let's go to Twilight. Twilight differentially private payment channel network. So first, let me introduce to you what our payment channel networks are. So from their name, it's the network, right? In network, we have the participants of the network. They are highlighted with blue circles. We call them relays. Relays are the participants in the network. Then we have channels, the red triangles, rectangles here. Channels is just a locked liquidity, locked coins. And what do I mean by locked coins? For example, with Alice and Bob, let's say that each one of them locked 5 coins in this specific edge. Now, when Alice wants to, for example, pass 2 coins to Bob, transfer 2 coins, then we can simply update the locked liquidity, the division of the locked funds. And now, instead of Alice having 5 coins, she has 3. And Bob, instead of having 5 coins, he has 7. That makes sense. We can just continue in doing that. Bob transfer 1 coin to Alice, and we will update the liquidity again. And here's an interesting thing. Let's say that in this state, when Alice tried to transfer 5 coins to Bob, it should be impossible, right? Because she doesn't have enough funds in their side of the channel. Okay, channels, edges in the graph. Very simple. Perfect. Route. Route is simply a list of channels from specific source to a specific target. For example, Alice and Bob don't have a direct edge between them in the graph, then we can just find a route. Payment is to use this route in order to transfer coins from the source to the target across the route. So, given an example, we have Alice, Bob, and Charlie. Alice wants to transfer 2 coins to Charlie, then we will just update the funds, just as before. Please note here that when Alice tried to do another transfer of 2 coins, although she has the liquidity in her direct channel, later in the route, there is not enough liquidity. So this will be impossible, right? Makes sense, right? Cool. Payment channel networks are not something that I just invented. This is a real genius construction that is currently being used. I think the main network that uses it is the Lightning Network. And it has around over $100 million locked coins inside this network. So this is a real thing, and this is big. A bit motivation about the question. Yeah.
So the entire networks are only one chain, or each edge we can have different chain. Like this is on Bitcoin, this is on Ethereum.
So that's an interesting question. I never thought about it. The Lightning Network is fully above Bitcoin.
Okay, sure.
And you're right, the motivation to PCNs are to improve blockchains. The question was about what chain is there, but I didn't yet talk about chains. So here is the greatest motivation, and that's okay if you don't understand this motivation. I'm not expecting from everyone to understand blockchains, but the idea is pretty simple. We use 2 transactions. The first one is to lock coins, and the second one is to use these locked coins and to divide them back to the parties. So by using just 2 transactions, we were able to somehow squish a lot of different transactions that happens in this network, right? Alice transfer money to Bob, transfer money back to Alice. Many things happened there, but we only use 2 transactions. So it somehow able us to do more with little number of transactions inside blockchains, which gives us better scaling, right? O of n transactions with just 2. The payments are pretty fast. We don't need to wait for many confirmations. And trust me, I will not prove it to you here, but we can do it in a trustless way, which means that if we want to transfer even across a very long route, we will not need to trust any entity in the route toward our target, which is great. The name dropping, but
do you need to know the list of the nodes along the path?
That's important question. So yeah, this is not inherent in the Lightning Network and in the network in PCNs that I'm going to consider doing this talk. Every node knows the whole network. Knows every edge and every entity, every relay. That's a very interesting question. I actually have another paper that discusses how to scale this using someone else that knows everything, and then you just query him for, hey, tell me what is the best route. There are problems there too. Think about incentives and which route it will give you. Good question. The name drop that I'll do here is HTLCs. That's the primitive that we will use for trustless. I will not get too far into it. And this is scaled because we're scaling blockchains. But, and this is where the things get interesting in this talk, because there is a very interesting attack on PCNs, which is an attack on the privacy. This attack is called the probing attack. It was presented in 2017. Probing, I didn't use this word, so Alex, I'll just use Google here, is to inquiring closely into something. And this attack is rather simple. In this attack, an attacker repeatedly queries channels to observe liquidity changes. So for example, let's consider the graph down below with a route of 3 channels. The 2 channels that are closest to the devil icon, I guess, are the attacker's channels. And there is another channel in the middle that is not belonging to the attacker at all. And the attacker knows that it has, let's assume that the attacker knows that it has 100 coins in one side of the channel. So we will just ask, hey, can I send 100 coins? And let's assume that he gets the answer yes. He will not execute a transaction because he don't want to really transfer this 100 coins. But then he will do that again. And he will get, again, yes, you can transfer 100 coins. And he will do it again and again until he will say no. Oh, what do you mean I can't transfer 100 coins? Something changed. Can I transfer 50? Using this method, the attacker will be able to know the existence of transaction. He knows that something changed. He will also know the size, right? Because he can do a simple binary search. If the attacker will do it for many channels across the network, he will also know who sent money to whom, because you can see the route. This is actually a very cheap attack, right? Because the attacker never finalized the transaction, and therefore money never transferred nowhere. So this is cheap. And Alice and Bob are not aware to anything that happened. So an external attacker can just execute queries to the network and identify that Alice paid Bob 3 coins at 10 a.m. Privacy problem. And here I'll go to our suggested solution. I know if you, this is, what's that? That's noise, I'm just kidding with you. So our solution is a new system that uses differential privacy, uses differential privacy in order to guarantee privacy. We realize we'll add noise, and we will use trusted execution environment in order to deal with selfish relays. I know that there are a lot of buzzwords that are underlined here, and everything that is underlined, I will explain later. In this paper, we did both analysis and simulations of the 3 properties that are the cost, the privacy, and the security, and we did a full prototype implementation. Let's dive into it. Cool. Because I don't have a lot of time, I will just highlight one work here. This is the work of the people that are here. That is a tremendously interesting paper that discuss theoretical bounds about this problem. So the first insight, in my opinion, this is the main insight of the paper, that there is a trade-off. There is a trade-off between the privacy and the utility of a channel, which means that if we want that the channels will not leak information about the transactions, we will somehow need to limit their utility or to make sure that they will not use all the locked coins that are there inside the channel. And that's an interesting approach. In their model, the attacker is passive, but it can look and see all the liquidities of all the channels in the network, which is interesting. Another thing that they do is in order to achieve their the limits, their upper and lower bounds, they assume they put limits on the attacker, and they assume that the attacker cannot correlate transaction patterns, which means that if there is a huge hub here of nodes and huge hub here of nodes, and every time this channel changes, then this channel also changes, they assume that the attacker cannot do that. And this is a limitation on the attacker that we, in our assumption, will not do it. But I think that another very cool citation that I'll put here is that I noticed that differential privacy is difficult to implement in our settings. And that's true. Differential privacy is indeed hard to implement in our settings, but this is what we try to do in our. Cool. So first, let me introduce you the notion of differential privacy. So in differential privacy, the idea is to distinguish between two events that happen. Specifically, in our paper, our notion to differential privacy is that the attacker will not be able to distinguish between two events. There was the event that Alice paid for, and there's the event that Alice didn't pay for. And we want that when the attacker observes the network, he will not be able to distinguish between these two events. We choose these specific events and not something like Alice paid Bob versus Alice paid Charlie, which is someone else, because we can use, this is relatively a simple one, and then later we can use something like composite theorem in order to create more complex events that we should be able to, that the attacker should be not able to distinguish between.
So here, the amount of the payment is irrelevant.
That's true. In our paper, we assume that all the transfer are of a constant size.
Oh.
So if you want to buy a bottle of Coke, then you will need to transfer 3 times $1 instead of 1.
Well, you can do binary representation.
That's true. So this is not inherent to the building. But you're right. Let me just put here the formal definition of differential privacy. So differential privacy has 2 parameters. There's the epsilon and the delta. Notice that, let's just find it here. Look at this phrase. So when epsilon goes to 0, there is no much difference between seeing an observation of the network given that Alice paid well and seeing the same observation when Alice did not pay well. So as epsilon goes to 0, these 2 probabilities looks the same. There is another error probability that is delta, in which there is a chance that the attacker will learn more than that, but this chance should be very small. The definition makes sense to all of you? Perfect. Noise. What is noise in our paper? Noise in our paper is simply a random number R that we will use in order to answer the question, can we transfer n coins? So when we want to ask, can we transfer n coins? We just take the coin liquidity, we subtract R, and then we ask, hey, is that enough liquidity? This is sad, right? Because we're subtracting R, we're subtracting a positive number, which means that we will be able to transfer less coins. This is exactly the utility trade-off that was discussed in the related work. I will later show how we can analyze it and to put real numbers on how much money do we lose, will they really lose, and how we can compensate him for this loss. Perfect. So when I say adding noise, I told you that we will sample some kind of R, some kind of random number, and I didn't tell you how we will do it. And one may think that simply just draw the noise independently for each word. Every time that someone asks for my liquidity, I will just sample from random generator independently. So this is a problem. This is a problem because the attack is very cheap, right? And the attacker can just re-execute the attack again and again and again. And given that he knows the histogram of the noise, he can just rebuild everything. So given that, let's say that he observes exactly 50% yes, then you can just write the formula on a paper and just solve it and to find out what is the real liquidity. And that's true not only for 50% yes, but also if he observes 75% yes, then he can always rebuild the histogram and understand what is the real liquidity. So the naive solution doesn't work. We want to do something that we didn't invited. It was published in 2013. And the idea here is that we want to somehow make the noise dependent. We want to drop the independency idea from the samples that the attacker sees over time. And the main idea here is the overtime. So let me just present you how we add noise, how we generate this art. I will not give you the full proof here, but I will give you enough intuition that I'm sure that all of you can later then just go and write the proof themselves. So, I have a question. I'm sorry. Any question?
Yes, I want to point out.
So the construction is fairly easy.
Hello.
Let's just divide the time into slots. Each timestamp is a leaf in the tree. Then we have the payments that are tracked in a subtree. For example, if we have a coin transfer at t = 2, all the nodes that are relevant to this timestamp will change their some count. Yeah.
Okay, so the nodes in this tree, are these the nodes over a particular path that you're sending a transaction, or what do these correspond to?
No, each channel has its own tree in its memory.
So this is time.
Yeah, so the x-axis here, the leaves in the tree are timestamps, different possibilities, times to query the channel. And this is just a way of how a specific channel needs to generate the noise.
And do you assume that you know like an upper bound on time, or can this tree grow?
So we assume that the time is can be represented in 64 bits.
Okay.
Yeah.
Did you mute your laptop? I think Ellen has a question remotely, but the volume is off.
Can
you try to ask
Hello,
now?
can you hear me?
Yeah, we can hear you.
Oh, I just want to mention this technique was first proposed in 2 papers, the work et al. And a paper by Chan Shi and Song in 2010-11-ish.
Oh, thank you. I will fix that. Thank you. I'll just try to hide it. Awesome. Let's continue. Now, the way that we derive the noise is using minimal covering set. So, for example, if you want to find what is the noise that I should return in t = 7, then I will consider all the time range between 0 to 6, and I will just consider what are the minimal covering set, which is the nodes, the minimal nodes that cover the whole time span. In this example, we just the nodes that are circled in blue are the nodes that cover all the time span between 0 and 6. For each such noise, we will sample noise once, which means that if we use the same node twice, this should use the same noise. Good. So to answer the question, can we transfer m coins at a specific time t? Note that we added this time to the question. The answer depends on the capacity of the channel, and then all the covering set of the time. These are the payments that actually occurred and the noise. Okay, did you understand the construction?
Just one question.
Yeah.
Why do you need this tree construction rather than just sample the noise each time, right?
Yeah, so sample the noise each time. That's a great question. This is exactly the name problem. When you just
not independence for each query, but each time slot.
Perfect. Then I will just at every time slot I will ask again, and I will get independent result. Then after 10 time slots, and time slots can be nanoseconds. So after a second, I will get 1,000 samples. That's not necessary. Perfect. Good question. And the very interesting thing is to ask why. Why do we use this complex construction? And let me just try and prove it to you in a minute. The idea is that I want to limit the number of different samples that the attacker gets for every coin transfer. And I'm actually assuming that the attacker queries all the time. In every timestamp, the attacker queries and gets information about what is the noise. So for example, if the coin transfer at timestamp t equals 1, and the attacker queries and timestamp t equals 2, then the minimal covering set will be the node that is circled in blue. Now, a 1 timestamp has passed, and the attacker queries again. The minimal covering set is the 2 nodes that are circled in blue. But note that the node that hides the key transfer that happens at t equals 1 is the same node, Therefore, we will not sample again. Perfect. Only when the attacker queries at time t equals 4, we will then sample again to hide the same coin transfer. So to finalize, we will sample in order to hide this coin transfer at t equals 1. We will sample the random generator only a few number of nodes, and this few number is the height of the tree. Does that make sense? Does that make sense why the attackers don't get enough observation on the noise in order to reconstruct the histogram, or to rebuild everything, to get high confidence on where are we in this histogram?
I mean, just to answer Minxin's question again, Minxin, this is the prefix sum mechanism we are using in our paper. This is just like
That's the intuition. You can always think about it as a prefix when the time is the prefix of the time. I don't know, timestamp. So you can see the timestamp as a list of binary, 0 and 1s, and then this is just a binary tree. Each node, actually, you can see it here. This is this 0, 0, 0, 0, 0. This is timestamps.
Sorry, quick clarification. So, sorry, actually, you had a question. Go ahead.
Would there ever be a case where we would be able to reconstruct this tree then, based on enough samples?
So that's interesting. If the attacker will be able to reconstruct the tree, to reconstruct the actual noise that happened here and the actual noise that happened here, then given a single sample, it will rebuild everything, right? Because he knows what is the noise here. So even if we will query here and know what is the noise, then he will just build everything. We assume that the random is generated both using the time, the node information inside the tree, but also on a secret that just the channel has, and it doesn't share it with anyone. And this secret is actually just could be computed in the beginning of time, and it just don't feel important to anything.
So with sorry, just a quick follow-up. Would multiple attackers receive the same noise?
The same noise, yeah.
I'm just going to sit with that for a second.
Sure.
I'm sorry, just a clarification. So every blue box here is, is it being generated as independent coin flip, or does a parent node have a relationship to its child nodes?
Independent coin flip.
Okay.
Yeah, that's deep. As Elaine said, there are two papers. She said 2 papers that were devoted. That's deep. That's a very cool work. And we just used it here in order to provide our differential privacy under the continual observation, which is exactly what we're trying to do.
And can you go back to the noisy equation, like the equation you actually output?
Of course.
You need another second to
device it. So capacity, when we are reducing the total number of payments, we get the liquidity, and then we're reducing the noise.
So
why the total payment is split into?
Just for because we I said that we track the payments in subtrees. So I just use this how many payments happen. So it's just more easy to see it like that. We can also, instead of writing the capacity minus the total payments, we could write here real liquidity at time t. So the same.
Sorry, what is the meaning of total payments at an intermediate node?
Yeah. So each node is rules a specific time step, right?
Oh, okay. So you're saying if it covers like time steps 0 through 3,
then all the transfer that happened in this.
Okay.
So this is actually the liquidity, right? The capacity minus what happens during this time. This is liquidity, but liquidity in time. Perfect.
I have a question. So, if the time, if I add like time 8 to this tree, then there will be 4 bits. So how do you extend this tree after the bits are extended?
So we assume that we don't.
You can have a large enough tree.
Yeah, our tree is very big. The tree is not really stored in the network, in the memory. We just recreated it every time because we can do it because this is inside a random generator. So we just use the node ID as a seed to the random generator. Our tree is huge. It has like 2 to the 64 bits, 2 to the 64 leaves. That's it. Perfect. Okay, thanks. Perfect. So
I have a question. So like, I guess you are suffering from the path length because each transaction will affect the whole path, right? So if the adversary is able to query every node on the path, then your epsilon needs to suffer from this path length.
So that's a great question. And the next slide is going to discuss exactly who is epsilon. So that's a very good question. As Elaine said, she's right. Every choice that we did here affects the privacy guarantees that we have, right? So a bit about our analysis. Our analysis first need to think about longer routes. When there is a longer route, there are many different channels, and each channel has new samples that the attacker can see on whether a transfer happened, yes or no. So in our analysis, we need to have the length of the route. This is L. We also need to consider how many routes are there between Alice and Bob. If between Alice and Bob there are 2 possible routes that Alice could use, then the attacker don't really know which one to query, right? So it helps us a bit. And let me just give you this not very helpful theorem that just use this L and R and the size of the tree and all the ideas to give an epsilon and delta differential privacy guarantee. And I'm sure that it doesn't help you because we don't really know as a human being how to read these things. So I will show real plots later.
Wait, why?
Sorry, can I actually look at that for a second?
Of course.
Yeah, why is the dependency on L is logarithmic?
Why would it be logarithmic?
No,
I think that we will take it offline.
It makes sense that it's linear.
yeah, again,
And just to emphasize, because we're already here, we take two very interesting worst case assumptions. And the first one is that the attacker queries all the time. He sees he's been there through all the timestamps throughout the time, and that he can query every channel directly, which is pretty strong. This is strong. Okay.
Sorry, I guess I don't understand this expression. Like, in the end, so you're saying epsilon is yeah, sorry, it's just this is too hard for me.
This is really too hard. I agree. I just wrote it to maybe to emphasize some kind of a wow effect, but I will show a plot. Trust me.
So it does suffer. It seems like it suffers linearly in the path length. And there's a term that's it's like everything's you're saying it's log of that.
That's true. The route length severely affects the privacy here, the guarantee that we suggest. And later I will show that in practice, the length of routes in real network is in the Lightning Network, for example, is relatively low, 4 in average. Thanks to the centrality of the Lightning Network, the very thing that everyone tried to overcome, we enjoy it because centrality means lower lengths routes.
What is T?
I'm sorry?
What is capital T?
That's the tree height. So that's the number of leaves. We have not a binary tree, but a tree with B nodes, B nodes for every node. And T is the number of leaves, is an upper value to type.
What is that mu and sigma without tilde?
Yeah, they're down there.
Yeah, I mean, like mu tilde is linear in L and mu, and what is that?
So this mu and this sigma is how we draw the noise for each node.
So like for each node, it's like Gaussian mu sigma.
Yeah. So
and
the theorem discuss. Let's assume that this node generates his nodes normally using mu and sigma.
Mm-hmm.
What will happen? Yeah, that will happen.
Do you remind me what B is here?
B is the number of nodes. I always talk about binary tree. So that's B equals 2.
Okay.
So yeah, but really, trust me. We will understand it more later. Trust me. But that's a great feedback for our next talks. So let's just a bit discuss about the trade-off. Adding noise means that we will fail more, right? We will say no to transaction that we might accept. We can compensate it by locking more coins, but then we need to lock more coins, which is a bummer.
So what I'm confused about is, can you go back to the previous slide?
Of course.
So I feel like, so M is the like the group privacy term, right?
So M is the.
If you do group privacy, normally there's a big blow up. So I don't understand how.
M is the payment size. You can take M equals 1. Let's assume that all the coins.
No, yeah, but M in general, it's like if you just use general group privacy, like M is like the group privacy parameter. And typically, if you use standard group privacy, there's a big blow up for the group with respect to the group privacy parameter. And I don't feel like, I feel like there's something, if you have this kind of guarantee, you are doing something very non-trivial and not just very non-trivial, and you're not just like using group privacy. Like the standard group privacy doesn't get you something so nice.
So I'll be happy to try and take it offline.
Okay.
I'm actually standing behind this theorem. I'm standing behind this theorem, but I want to keep and talk about different things.
Mm-hmm.
Okay? Perfect. Great. So we said that adding noise means to fail more, and so either fail more or lock more coins. But extra locked coins, so that's the cons. The pros are that the extra coins that we're locking at the beginning of the channel will be there at the end. So we only conceptually pay. So if we will take a loan for these extra coins, we will pay it back when the coins will release, but we may need to pay for its interest rate or something like that. And another thing to say here is that our network offers better service, and we're regular to pay more for better services. So here is the plot that I promised for you, which trying to say how many additional locked coins there should be in order to achieve which level of privacy. Okay, so the epsilon here is the epsilon here. This is the definition of differential privacy. And that's an interesting plot because so this one we get from our analysis, but on the other hand, we can achieve the same graph when we do an actual simulation and to try to understand, given that there is a random coins that goes back and forth, demands to one side or demand to the other side, what is the fail rate and how much do we need to lock extra in order to get a specific fail rate, which is the delta that we discussed. So we get the actual same result from both simulations and the analysis. And I think that the bottom line that is interesting to say here is that you need to lock much more coins, right? To lock 10,000 extra coins. And these extra coins that should be locked are expensive. But given that you just can take loan and repay it back and then just paying for the interest, then given that you have 77 payments a day, at least, you just need to collect 1% fee, and that's okay. It will cover everything. So it might sound like a very high demand to lock a lot of coins, but this will pay itself pretty fast.
I'm still confused. You talk about your transaction size is constant. So, yeah. So here, can we assume the constant size is 1?
Yeah, absolutely. Yeah, there are many parameters that I'm hiding from you here. The constant size, the payment constant size, I'm also hiding from you delta. Okay. That's true. In the real paper, this plot is more complex. There are many different plots on the same figure.
Yeah, I just feel a little bit, not very convinced that if you need to have like 10,000 additional coins for a constant size transaction, is that paid, or how would the cost be covered so fast? It's just I don't know how to calculate this
So another things that I'm hiding from you here is an assumption that the yearly interest rate is 3%, and then you can just do the computation. Really.
Okay.
That's back of the envelope. That's pretty easy.
A question? So, who is responsible for adding these locked coins? The relays or the sender or receiver?
The relays. Each relay, me as a service provider, I need to provide better service, which means that I need to lock more coins. Me as a service provider need to pay for better service. I will give you better service. I will ask for more fee for it, but it will cost me. Perfect. I will go over it because we don't have time. Another challenge that I want to highlight here, because I really find it fascinating.
Can I ask a question about the threat model? So basically, you don't secure against the relays themselves, right? You only passive probers.
Yeah, the relays are passive. That's true.
But the relays themselves cannot. They can see the exact amount, right? You're not securing against the relays. The relays, not the attackers.
That's a great question. You are absolutely right. But given my next few slides, I will show you that they will not know the exact liquidity till the end. And you're right, this is an important question. There is an inherent problem in here. The inherent problem is that relays are selfish and they don't want to add noise. They might tell you that they add noise, but they don't want to do it because they will say no to more transactions that they would otherwise have accepted, right? So we want to somehow force them to add this noise. We actually thought a lot about incentives, and going to forces our last way back. And when I'm saying force, this is not force and not this force, but this crazy force that is called T's. Anyone here knows what T's are? Perfect. That's why I have the next slide. T's. What are T's? Trusted execution environments. So basically, T's are isolated hardware. You can think about it as another CPU and another memory in your computer. You would think, oh, how can you assume this thing? And I can assume this thing because Intel, since 3 years ago, put 30, which is an SGX, in all their processors. So if you have a computer that is younger than 3, you have T in your computer. This offers us two very interesting properties. The first one is confidentiality. The confidentiality means that this CPU and this memory, you cannot see what happens there. So if it executes a specific opcode, you will not know it. If there is a specific key in the memory, you will not be able to read it. And it also promises integrity. Integrity means that if it tells you that it runs this specific program, this program cannot be changed during runtime, which means that it can tell you what it ran and you cannot interfere it, and you cannot know what really happens during this execution. It seems like I don't have enough time. So I just highlight that it creates a lot of problem, and we just needed to somehow solve all this problem. All the details are in the paper. Yeah.
How do you, if the relays are all running TE, they need to attest to the correctness of their noise addition. Is there like a registration process when they first join the network and become relays?
Yes.
Okay.
When a relay wants to register to the network, his T need to perform a remote attestation to another T in the network, and then you get the certificate or a private key that helps him to communicate with the rest of the network privately.
So you're like bootstrapping on them?
Yes.
One.
Yes. I really just don't have the time to get into it, but that's interesting. Let me just, great, I have 5 minutes, so I will just discuss the implementation. Because of the T, we need to encrypt everything, because without encrypting, the attacker, a relay will be able to just run the T over and over again. So we need to encrypt everything, which means that we need to change the primitive that I called in HTLC. We now need to change it to something else. So we need to first implement some difficult, different smart contracts specifically for that. And we did it in Solidity and tested with, Solidity is the language of Ethereum. And we tested it with Ganache, which is a local blockchain. The enclave is obviously an SGX. So, and it communicates only, it can read only CPP programs. So we wrote it in CPP using Pistachio in order to communicate between the enclave and the relay. And the relay was written using FastAPI in order to be fast enough. And we use just PyCryptodome because we don't want to implement any crypto ourselves. We ran it all on Azure Confidential Computing, which gives us actually infinite number of SGX and machines, which is great. We use Azure SDK because we want to create some kind of a real world simulation. So we had dozens of machines in different regions, and we just need somehow to that will manage all this operation. And we use Elasticsearch in order to grab some aggregated metrics in order to do performance improvements and things like that. This creates a very cool open source that includes maybe all the languages that I know. And you can just see it in here because this is open source. And here are the results. Regarding the throughput, we reached to a throughput of about 850 payments per second. The current Lightning Network is at around 350, which is great. We found that the bottleneck is the T, which is pretty interesting because we didn't have any assumption on the relay, so we just parallelized everything. But once you need to talk with the T, we assume that there is a single T, which is a single bottleneck. The latency is also extremely fast.
Sorry, yeah. Why were you able to get better throughput than the non-private current version?
Because we worked on it. Okay. That's the real answer. I really think it makes no sense that Lightning could not be better. Okay. But we really tried to.
Because with Weisha, we played with the Lightning code base before, and had a lot of trouble with it.
Yeah, I did it as well. There is a bad performance there. They can make it better, but the idea is that the current demand don't need it.
So you just implemented your own, an entire new.
Yeah.
Nice. Yeah, that makes sense.
Yeah. The latency is also extremely fast. With 4 relays, we got a latency of less than 1 second to finalize the payment, which is pretty cool because this is a bit, we're doubling the natural network speed because there's, we did communication between, I think, Europe and North US. So just doing all these packet transfers takes time, and we just double it, which is pretty cool. So less than 1 second latency for relays. And another very interesting thing to notice here is that when you need to, I said that we implement a new smart contract, which means that there is a new cost that you need to put something encrypted inside the blockchain. And then, so it costs you storage. And then you need to decrypt this private thing, which costs you gas. So all these things cost money. And there is a very interesting trade-off that we that we had between this computation that should happen inside a blockchain to the computation that should happen inside a T. We put more work on the T to reduce work from the smart contract. I will not get too deep into here, but this is our choice. It could look differently where this is higher, but this is also higher. So that's an implementation choice. I will conclude in my last minute. We were able to achieve differential privacy using under continual observation. Privacy comes with the cost. We need to pay more in order to achieve the privacy that we want. Selfish relays are problematic, but we can force them to use our protocol and make sure that they noise their channels using TIS, and we have a full prototype implementation. That's it.
So I guess also Kati has a few works on designing privacy-preserving payment channels. Can you compare your approach with their approaches? Like I don't know their papers very well. I just happen to know that he has some works in the space.
Who specifically?
Kati and his students.
Yeah. So actually, just before this talk, I dropped the related work slide is much more rich than mentioning only this work, your work. So yeah, we can compare ourselves to other suggestions. Specifically, their suggestion assumes a passive attacker and has a problem of deadlocks. So because they want to limit the number of concurrent payments, they have problem of deadlocks that we don't have. And actually in the paper, we did a much more thorough comparison between the two. We actually compared ourselves to everyone that we know. If there is someone new, I will be happy to read it and to do another comparison.
So just at a very high level, are they also trying to achieve differential privacy, or they have different?
If I remember correctly, they have different notion of privacy.
I think, is this like, are they trying to keep the relay from inferring who the source and destination are? Or maybe I'm confusing it with the
I think that they also trying to solve the probing attack, which is to find transaction size and its existence. So
have you considered a case where the prober is also a relay?
That's a great question. So yeah, if one of the relays is an attacker that's trying to execute probing attack, then he will know what is his liquidity, but nothing more. So he will have more observation over the network, but not, which is, well, not worse than today. That's it.
Okay, but with each increase in probers and relays, then you do get more information from the system. At what point would you be able to crack the system?
So that's an important question. That's actually related to how many routes going through you, and this is something that is hard to say. So you need, that's possible, but I would say that this is inherent. That's inherent that you will be able to know what is my money, because you need to, in the end, you locked money, and in the end, you need to unlock the money and get it. So this is inherent that you will know how much money do you have. So no matter what will happen, which kind of privacy we will create in these PCNs, eventually you will know that money transferred from you. So you will know it in the end.
You know about yourself, but
yes, on yourself.
But I guess the question is, like, let's say we have a network of, we'll just keep it small, like 20 people, and 5 of them are relays and brokers.
So it really depends on the topology. If these 5 people are in the center and all the rest just moving all the transactions through them, then they have all the observations that they need. But if they are in satellites, then nothing goes to them. So it really depends.
I'm thinking about other examples.
That's awesome. So actually that's related to the other paper that I mentioned in the beginning of an attacker that creates new channels to the network in order to hijack all the traffic to go through them. That's right. You can use this paper here and to break this one. Yeah.
Okay.
But again, this is a lot about the routing algorithms. If the routing algorithm will be changed, we should reconsider. More questions? Perfect. Thank you so much.